Hello, I'm going to talk you about power in three-phase systems. I presented before that the complex power is equal to the voltage times the conjugate of the current, but the effective value or RMS value. Keeping this in mind, so it's easy to see that for one circuit A, we can compute what is the active or average power in terms of the absolute value of the line to neutral voltage, line current, and the difference of phase angle of the voltage and current sinusoidal waves. If we have a three-phase system which is balanced, we know like the magnitude, they are always equal and we call BF. And we have something similar for the current. So three of them, they are equal. We're going to call I phi. So this is the current that goes through the phase A. Here's the voltage for the phase A. The difference of angles is going to be defined by theta phi. It's easy to see like that this difference is equal in any kind of two pair of phases. So given these definitions, so we can say the power in one phase will be the voltage in this phase times the current in this phase times the cosine of theta phi. And of course, so this is the same for each of these phases. So we are assuming balanced systems. So we are expecting that power in A, power in B, and power in C are the same. So now if we want to compute how much power are we sending to this load of three part which is connected in Y star, the answer is easy. So you just multiply by 3 the power that we are sending in one phase. The total power is equal to 3 times, this is equal to 3 times the power that we are sending just in one phase. We can also write this with regard to the values of a line. So for example, the current in a phase is equal to the current in a line. So we keep this one is equal to the voltage line or line to line divided by square root of 3. So just multiply by 3. So we work out this square root of 3 and 3. We keep this value as a total power. So the total power is equal to the voltage line to line, which is the typical voltage that you see in the specification of every machines or the data that you have from transmission line, etc. So IL is the current through the line, and this is the difference of angles. And of course, so we have this square root of 3. This is the total power that we are sending to a balanced load. Now let's see what happens when we have a delta configuration. We understand like this C delta are the same. This system is balanced. So we can again define what is the power that we are sending through phase A. Power that going to be received in this load by the phase A is equal to the voltage between A and B, the current between A and B. So you see this is what is affecting to this load. This is the power which is where it's consumed. In this delta configuration, remember, voltage between line to line is equal to what we define voltage phase. In this case, the current between line to line is equal also to the current in this phase. And we again define this theta as a difference between voltage between these two signals. Well, if we compute what is the total power, so the total power in this case for one phase will be, so this VAB, which is equal to this B phi here, the current through the phase here, and finally this cosine. And then again, we can actually work with these values and we observe, so if you observe multiply by 3, so this is 3 times the power of a phase, and we end up with the same formulation. So this is very interesting thing. The interesting thing here is, well, no matter if your load is in Y configuration or delta configuration, the power that you are sending is always the same. This is very good and very nice. So power doesn't depend on the load configuration. So let me recap what we have seen here. So we see like this power, total power in a three-phase system is equal to the voltage time current. This is very similar to the DC case, but now we have something else. So we have this square root of 3, this is new. And then of course, so we have this cosine of phi. So because we have sinusoidal wave and this is somehow is scaling. We can work formulas in similar way for calculating what is the reactive power. We come up with the same formulation, but instead of having a cosine, we have a sine. And of course, we can compose what is the complex power for a system. So the total complex power that we are sending in a system is 3 times the power we are sending through a phase. And this is, again, square root of 3 BL IL using the phase theta phi. Then finally, I would like to compute the instantaneous power in a three-phase circuit. If you remember, when we have only one phase system, the instantaneous power is a sinusoidal signal. Sometimes it can take positive value, sometimes it can take negative value. If an average is positive, it means like we are delivering some energy that can be transformed in other type of energies. So I would like to now compute what is the instantaneous power for these three phases. So I can basically start with the phase A, and then this is in time domain. This is why we are using the lowercase. It will be the signal of the voltage in time domain times the signal of the current in time domain. By doing so we have this definition. This is simple if you work with expression of instantaneous power for a circuit. It is also very easy to do for the other two phases. But we are interested in the total power, instantaneous total power. So if we are summing up these three signals, we got this expression. So 1.5 times the voltage and current, the amplitude of the sinusoidal wave, times cosine of the theta. This instantaneous power for every phase depends on t. You see here dependence on t, while the total power doesn't depend on t. So this is very interesting. So we have a three-phase system that is sending power, which is a sinusoidal wave, but the summation of the total power is a positive value, but it doesn't change over the time. If you want to design a motor, you will probably prefer to have a constant torque if the power is changing over the time, so this torque also is changing over the time. But if we use the three phases to fit this motor, so we can design this motor in such a way the power is always constant.